Hi guys, in this video we are going to introduce the concept of enthalpy and formation and how we can use this concept to determine enthalpies of reactions for any given reaction. In order to do this, we're going to have to introduce this concept of a standard state. And when we move through the concept of a standard state, I want you guys to think about our analogy of altitude that we presented earlier when we were discussing the concept of a state function. So recall, state functions only depend on the initial and final state. We don't care about the path that we need to travel to go, between the two states. And so we can talk about the change in altitude. For example, if you're climbing Mount Kilimanjaro here, some 19,000 feet, no matter what path you take, you're still going to have the same change in altitude if you go from the base all the way up to the summit, right? And so, of course, when we are measuring the altitude of any given mountain or any altitude in general, we've agreed upon sea level as being our 0 point, and then we talk about changes in altitude, relative to that 0 point of sea level. So the first thing we're going to do here is actually kind of play the same sort of game in the context of elements and atoms and compounds. We are going to define the so-called standard state of these elements, assign that a 0 for enthalpy, and then look at changes therefrom. So to get a feel for what I'm talking about here, I want you to see sort of the big picture, and then we're going to go back and dissect essentially this whole diagram here. So if we consider our combustion reaction of methane, we've seen many times in the course so far, we can start off here with our reactants. And the idea here is to break apart these reactants into their most stable elemental forms right up here on the top, and then once you've broken it apart into these most stable elemental forms, then take those individual elements and build up the products that we care about, CO2 and the H2O, and then look at the overall change in reaction associated with decomposing all the reactants and then forming all of the products. Once you do that, you can get an idea here in purple for the overall delta H of the reaction. Okay, so this line up here, this is kind of serving as our sea level, our 0 point. Okay, we're measuring all these delta H's relative to that. Okay, so the reactants broken down to form go back down to sea level, right, or up in this case. And then we are forming these different products here in red, which are again being formed from those individual elements here at our sea level. Okay, so now let's go ahead and start dissecting this process in more detail. So first off, it's important to keep in mind that all of these thermodynamic variables that we've talked about and that will be presented in future courses here, they vary with conditions. Okay, so when we're introducing the concept of enthalpy or some sort of change in enthalpy that's associated with a given process, the magnitude of that enthalpy change will vary with temperature, pressure, concentration, and these sorts of things. So if we want to have a nice way to discuss changes in enthalpy and compare changes in enthalpy between different substances and compounds, we need to come up with a standard, all right? And so this standard state, and again, is going to help us in the analogy to come up with this sort of sea level that we can relate all these other changes to. So the first definition here is the so-called standard state definition, and the standard state for a gas is simply 1 atmosphere of pressure, and we assume ideal behavior. Okay. For a substance in aqueous solution, right, then we're going to assume a 1 molar concentration for standard state. And for pure substances, we're going to look at the most stable form, right, of that substance at 1 atmosphere of pressure and the temperature of interest. What we're going to use for this course, and what's oftentimes used in literature, is a temperature of 298 Kelvin, right? And whenever we're in the standard state, we're going to use this little degree symbol to indicate that whatever quantity we're referencing with that degree symbol has been measured with all of the substances in their standard state. And so then, with this definition of standard states in place, we can talk about the standard enthalpy of reaction, which is simply the enthalpy change of a reaction that's measured at the standard state, okay? And we're going to denote this standard enthalpy of reaction as delta H reaction like we have before, but we're going to again introduce that little degree symbol up there to denote the standard conditions. Now, related to the standard enthalpy change for a reaction is this concept of a standard enthalpy of formation, okay? So the standard enthalpy of formation, also called a standard heat of formation, okay, is the enthalpy change for the formation equation when all of the substances are in their standard states, okay? So as an example here, let's look at the formation of methane. So the formation equation for methane, all right, is written as we have right down here, okay? We are forming 1 mole of whatever substance is of interest here. And so that's one of the criteria that we have for writing these standard enthalpies of formations. Just for ease of comparison with other compounds, we always assume 1 mole of that compound of interest is being formed, okay? And then we form that compound of interest from its respective elements in their most stable form, okay? And we're assuming everything is in the standard state. So if everything's in the standard state, we have these elemental forms in their most stable form, right? And we have all of these conditions being met of 1 atmosphere pressure, 1 molar concentration. In this case, we're not dealing with a concentration here, and 298 Kelvin is the temperature. Okay. So a couple notes here. So for any element in its standard state, well, remember the definition of the standard state. That was our sea level here. That is the 0 point. So as a result, the enthalpies of formation for, in this case, the graphite and H2 are 0, right? They are already at sea level. The standard state for molecular elements, for example, halogens, and a few other guys we'll talk about, N2, O2, and the like. The molecular form, right, is the most stable state. Okay, so the standard state is going to be Cl2, right, for chlorine, and so Cl2 has an enthalpy of formation of 0. And if you break it apart and you look at just the individual chlorine atom, well, then the enthalpy of formation of that individual chlorine atom has positive 121 kilojoules per mole value. Okay. So these, the most stable form of different elements, this is something that we will end up giving to you in the course of in the context of a table that we'll explore, shortly here. So it's not something that you have to memorize what these are, but you want to keep in mind that the most stable form of different elements depends on the properties of that element, its behavior, its characteristics, and in the case of O2, N2, Cl2, Br2, I2, right, a lot of these gases that we've talked about already, their most stable form, you have to remember, is that diatomic form with the enthalpy of formation 0. And then a final note that I'll make is, most compounds, I'm going to say most compounds have a negative delta H of formation. In other words, most compounds are below sea level, if we were to use our analogy from before. So once you form a compound, you're basically going below sea level there for most compounds. In other words, there's an exothermic formation reaction involved with that formation of the compound. So heat is released when most compounds form from their elements, okay? But the key word there is most, right? There are a handful of exceptions, and once again, those exceptions would be noted, in a table. So let's go ahead and take a look at that table then. So here's a typical sort of table that you would see that could be provided for you on an exam, for example, that's looking at the standard enthalpies of formation at 298 Kelvin. And so if we go through here, we can look, one of the first examples we just talked about were these diatomic gases, right? And we saw how Br2, well, first of all, Br, right, is not the most stable form for bromine, right? The most stable form for bromine is the Br2 form, okay? And it turns out here that for bromine, elemental bromine, right, the most stable form of bromine with a corresponding enthalpy of formation of 0 is Br2 in the liquid state, okay? A lot of times when we're dealing with metals, right, metals show up as, just that elemental metal, for example, calcium solid here, and those metals, pure solids, are going to be the most stable form. Graphite is the most stable form for carbon. It's actually a little bit more stable than the diamond here. And we can zoom ahead here, point out a couple other metals here. So we notice that sodium, for example, most stable form is 0. We talked about a couple gases, N2 gas, O2 gas previously. Those are both 0. Okay, so we're kind of getting a feel for where our sea level lies. H2 gas as well. Okay, Cl2 gas. Okay, and then notice that a lot of these different compounds do have negative enthalpies of formation. Okay, so there's a lot of negatives showing up as we go down the list, but there are also a handful of exceptions. Okay, so for example, this guy right here, right, C2H4. It's got a positive enthalpy of formation, and a couple other positive enthalpies of formation, showing up as well, right? But suffice it to say that the vast majority of compounds do have a negative enthalpy of formation. Okay, so then let's see, using these tables on the chart, we can go back and start to make some more sense of the initial diagram that we were looking at. Okay, if we go back to that diagram, we see that O2 gas has an enthalpy of formation of 0, which means O2 gas is already the most stable form. So when we're breaking apart our reactants, O2 gas just remains O2 gas. Now if we go back to the table and we look at CH4, methane gas, we see that the enthalpy of formation for methane gas is minus 74.6. So using that value, we come back over here and we say, well, that was formation. If we take CH4 and break it apart into graphite and hydrogen gas, most stable form of hydrogen, then we're going to be taking the opposite sign of that. So we're taking the opposite sign of the reactants, right? That because we're now breaking apart, decomposing those reactants to go into their constituent elements, and then we are going to now take all of these compounds and their elements in their most stable form and form compounds, the product compounds, from these. And so if we go back to the table, you can double check it for yourself. CO2 gas is a minus 393.5. H2O gas, right? This one's worth taking a closer look at, because this is a common mistake that students will make. Actually, there's two common mistakes embedded in that part of the problem here. Notice that H2O shows up twice, right? One is a gas, one is a liquid. So when we were referencing these compounds on this standard enthalpies of formation table, we need to not only look for the identity of compound, but also the state in which that compound is formed. So we're looking at H2 gas, right, or H2O gas rather. So we're going to be taking this value minus 241.8. But now remember, right, when we are forming our final products here, H2O gas, there are two of them. Okay, so this represents 2 times the standard enthalpy of formation of H2O gas. Okay, so that's why that value is double the value that we see on the table. Okay, and so we can see in this way we've started off with reactants, broken apart into individual atoms and elements in their most stable form, and then built up our products. Okay, and we know from this table now all these delta H's associated with the formation, or in this case decomposition of reactants, and as a result we can add and subtract all these terms as needed and come up with an overall delta H of reaction. So to see this in practice and kind of work through every step now, let's look at basically an equation that allows us to directly move towards a solution for solving a problem like this. So the same problem we have on the previous slide here, we're combusting methane gas. Okay, so it turns out the formula that we're effectively following here when we're looking through that diagram is given right here on the first line. What we're basically doing is summing up the enthalpies of formation of all the products, because remember, we're going from individual these elements in their most stable form, and we are forming products. Okay, and then we're going to subtract off the enthalpy of formation of reactants. Okay, now it's very important to remember that negative term there. Okay, this term it's a minus the sum of the enthalpies of formation for the reactants, because the reactants are being decomposed, just like we saw here for methane here, right? We're breaking methane apart into the individual elements. Okay, and so the energy associated with that decomposition, right, is obviously going to be the same magnitude as the formation, because it's just the opposite direction, like we saw in the previous lecture, right? However, it's going to be the opposite sign. Okay, so same magnitude, opposite sign. So that's why we have a negative, right here, minus reactants. Okay, so once we have that laid out, we also have to, I want to draw your attention to these little coefficients. The stoichiometric coefficients must be included in this equation. So not only are you looking at the enthalpy of formation of the products and reactants, but you're also multiplying those respective enthalpies of formation by the stoichiometric coefficients in the problem. So let's crank through this then. So we're looking at our products in blue here first. So we're going to be having to pull from the table the enthalpy of formation of CO2 gas. The stoichiometric coefficient here is 1, so we have a 1 in front. Then for our next product, we have H2O gas. So we're going to have H2O gas, enthalpy of formation of H2O gas, which we'll pull from the table. And now we are using this stoichiometric coefficient of 2, right? Because we have a stoichiometric coefficient of 2 in the balanced chemical reaction equation. Okay. Now we're going to subtract the enthalpies of formation of the reactants. Okay. So the first reactant here is methane, and methane, right, has enthalpy of formation obtained from the table, and now we're going to put a negative sign right there because it's a reactant. Similarly, we're going to subtract off 2 times the enthalpy of formation of H2O gas, because we have a stoichiometric coefficient of 2. Okay, so then we turn back to the table, and I encourage you guys to verify all these numbers. The enthalpy of formation for CO2, for H2O gas, and then the enthalpy of formation of our methane, right? And remember, the enthalpy of formation for methane is negative, but it's going to be minus a negative. And then the enthalpy of formation of O2 gas, which is in its most stable form, which is 0. And adding all these terms together, we arrive at our delta H of reaction. So at this point, I hope what you're seeing is that using these tabulated values, which I've collected here for ease of reference, gives you a really direct way to simply plug in to a relatively simple equation here, products minus reactants, and ultimately allows you to find delta H of reaction. So we've talked about using calorimetry to find delta H of reaction, using a handful of known reactions that we can massage around, add together, using Hess's law to find delta H of reaction. And I think what you'll find is that by just writing out this little formula and referencing a few values from a table, this is perhaps one of the easiest, more direct ways of finding delta H of reaction. Okay, so once you do a couple of these problems, I think this will be your preferred method to find delta H of reaction. Just a quick word of warning, however, there's some challenges associated with finding these enthalpies of formations experimentally. And so what you will see at times is even different values of these thermodynamic quantities reported from different sources. Okay, and so it's not uncommon for you to maybe be working on a problem with one table, your lab mate working on the problem with another thermodynamic values table, and you guys end up with answers that are a few kilojoules per mole off. And so if that happens, just know that it is a result of experimental uncertainty in these measured values. And so as a result, this isn't necessarily the most accurate approach for finding these thermodynamic quantities, but it does a very good job of getting you close to that number quickly and easily. And once we have that delta H of reaction, right, then we now can complete thermochemical equations relatively quickly. And just a reminder, when I write down that minus 802.5 kilojoules, we know it's an exothermic reaction, right? And this is the energy associated with combusting 1 mole of methane with 2 moles of oxygen to form 1 mole of CO2 and 2 moles of H2O. Okay, so that all that we learned about regarding thermochemical equations still holds. Okay, so to sum things up, what we've talked about here in this lecture is this concept of standard enthalpies of reaction by introducing this concept of a standard state and the concept of standard enthalpies of formation. Okay, so the standard enthalpy of formation is the enthalpy associated with forming a given compound from its individual elements in their most stable form. Okay? And by introducing that concept, we can find delta H of reaction for literally any reaction by taking those reactants, right, decomposing those reactants into the individual elements in their most stable form, and we can figure out the enthalpy change associated with that process by taking the negative of the delta H of formation, so negative delta H of formation for those reactants, and don't forget those coefficients, stoichiometric coefficients, to represent the number of moles of each one of those reactants. Then once we form those elements, we are then going to take those elements, put them together to form compounds, and however many compounds you might have, you'll just add all those enthalpies of formation together, and you'll end up with your products. And the enthalpy of formation, for each one of those products, all summed together, shows up right here with those stoichiometric coefficients. Add all those terms together, and you have your enthalpy of formation, standard enthalpy of reaction.